Today I will be going over my lab report for Lab 2, which involves analyzing an object in projectile motion. This experiment involves observing an object moving in projectile motion and creating x position versus y position graphs. The ultimate purpose is to have a graph where we can compare the lines from the data from the GlowScript modeled predictions and the actual real-world tracker data. The GlowScript modeled predictions predicted the motion of the graph in two scenarios, one where gravity is the only force acting on the object and one where both gravity and drag are acting on the object. The graphs revealed that the model that only incorporated gravity predicted the highest vertical height that the object reaches. Let's dive deeper into some of the core concepts covered in the lab. The lab covers projectile motion, which is defined as the path an object takes when it's only subject to gravity near the surface of the Earth. For the sake of this class, air resistance and drag due to air resistance aren't considered when solving problems. Kinematics equations are used to solve for quantities such as position, velocity, and acceleration. Kinematics equations can only be used when there's a constant acceleration, such as the force of gravity. Usually when solving projectile motion problems, there's no horizontal acceleration, and gravity is the only source of vertical acceleration. In the real world, both gravity and drag act on objects in projectile motion, but in the experiment, drag was only considered in one of the modeled simulations. In all three experimental settings, our initial was 0.1905 meters in the x direction and negative 0.002417 meters in the y direction. B initial was 1.844 meters per second in the x direction and 4.44 meters per second in the y direction. The mass of the object was also 0.0029 kilograms. However, in the GlowScript model with drag, F net was drag force minus gravitational force, and the B value used to calculate drag was 0.007035. In the simulation without drag force, F net was calculated with just the force of gravity. Delta T in both simulations was 0.033333333 seconds. The system in this experiment is a piece of paper, and the surroundings are the earth, air, and the hand throwing the piece of paper. When creating the modeled prediction, GlowScript was used to code the simulation for this experiment. The initial position and velocities are instantiated, and the position and velocity update formulas are used to update the position time and velocity time graphs. The position update formula is initial position plus velocity times delta t, and the velocity update formula is initial velocity plus net force divided by mass times delta t. The code used iteration to create an accurate position versus time graph. In the simulation that incorporated drag, the net force isn't constant. However, in the simulation without drag, the net force is constant. The graphs of the trajectories are featured on this slide. In the actual experiment, the object used was a crumpled piece of paper, and a meter stick was used for calibration. The tracker was the graphing software used to plot the actual data. A video was taken of an object being thrown and ended when the object went through the projectile trajectory at the same height it was thrown at. We uploaded the video into Tracker and trimmed it so the video only featured the part where the object was in projectile motion. We set the position axis at the origin, being at the center of mass of the crumpled paper at its initial position. Tracker was able to create a linear regression for the x position versus time graph, reaffirming that the object traveled at constant velocity in the x direction. Tracker used the polynomial regression for the y position versus time graph, thus showing that there was acceleration in the y direction. Now moving on to the comparison. Between the three graphs, they were similar because all graphs followed a polynomial regression and the object traveled approximately the same horizontal distance. However, in the y direction, all three graphs had different maximum heights. The graph in the modeled prediction without drag had the highest maximum vertical height, likely because it considered the least amount of forces. The tracker graph had the next highest vertical height, followed by the modeled prediction of the graph that did consider drag. Additionally, the velocities were all different, as shown with the different equations to depict the trajectories. To address some sources of error, the video uploaded into Tracker was not likely trimmed perfectly, where the object gets launched and lands at the same height. This could explain why the tracker graph isn't a perfect symmetrical parabola, and it starts at a different height that it lands at. Now moving on to the what-if question. What if the object was thrown straight up at the same initial speed? Would it spend more or less time in the air compared to the projectile? The object would spend more time in the air when thrown straight up. This is because the vertical component of the initial velocity determines the time in the air. The projectile object has a smaller initial vertical velocity since it's thrown at an angle, and its initial velocity has to be split up into two components accordingly. For the object thrown straight up, however, the initial velocity is only acting in the y direction. So what does this all mean? Do any of our models predict that the object reaches a terminal velocity? None of the models predict that the crumpled paper reaches terminal velocity. The tracker graph and the GlowScript graph of the model that incorporated drag had an exponential velocity versus time graph that didn't have a clear asymptote, so it can be concluded that the terminal velocity wasn't reached. In the model that didn't account for drag, the velocity versus time graph was linear and also didn't indicate any terminal velocity. One way we could test for terminal velocity would be if we dropped a crumpled piece of paper from a high platform and recorded it as it fell. We would upload the video into Tracker and generate a velocity versus time graph. And if the paper spent a long enough time in the air, the velocity versus time graph would have a clear asymptote that indicates that it reaches terminal. In conclusion, the modeled prediction that didn't incorporate drag had the highest Y max prediction, likely because there's no drag slowing down the paper on the way up, allowing it to reach a higher max height. Thank you for listening.